Two oceans just broke the forecast. The Pacific is running one of the strongest El Niños in recorded history. At the same time, a cold scar appeared in the Atlantic, a band of water 2 to 5 degrees Fahrenheit below normal, stretching from the African coast toward Brazil. Only the sixth event of its kind in over 40 years. One record warm, one rare cold. Every instinct says they should fight each other, the atmosphere splitting the difference somewhere in the middle. They do not cancel, they add. Both anomalies push the atmosphere in exactly the same direction, and the result has already forced forecasters to tear up their hurricane predictions and start from scratch. We have two of the planet's biggest ocean patterns firing simultaneously, in opposite directions, in different oceans, and the atmosphere is treating them as allies. Let's talk about why. First, the name everyone is using for this is wrong, and it will confuse everything that follows if we do not fix it now. La Niña, properly speaking, lives in the Pacific. She is the cold phase of the same oscillation that produces El Niño, and by definition, you cannot run both at the same time in the same ocean. When one is on, the other is off, full stop. What is happening in the Atlantic is a different animal with its own name, the Atlantic zonal mode. Zonal means along lines of latitude, and that is exactly what it looks like on a map. A band running east to west along the equator. Like its Pacific cousin, it swings between a warm phase and a cold phase every few years, and the cold phase gets called the Atlantic Niña. Similar name, different ocean, different physics, different consequences. So we are not looking at El Niño and La Niña at the same time, strictly. We are looking at El Niño in the Pacific and its Atlantic cousin running cold simultaneously, which is arguably stranger, because the Atlantic version is far less studied, far less predictable, and almost nobody outside the field knows it exists. Now, why would an entire ocean basin fly under the radar? Because we are bad at it. Not casually bad, systematically bad. Every major climate model, every generation, including the current one, runs the tropical Atlantic too warm. The bias appears within the first month of a seasonal forecast and reaches 80% of its full magnitude within 6. And because that warm bias suppresses exactly the cold tongue that defines the Atlantic zonal mode, our models are demonstrably poor at reproducing the pattern we need them to forecast. We are watching a rare event in the one ocean basin where our tools are known to be least reliable. That should make us both very attentive and very humble about what comes next. But first, we need to understand how the cold gets there in the first place. Here is the counterintuitive part. The eastern equatorial Atlantic reaches its coldest temperatures in July and August, the middle of northern summer, when the sun is at its strongest overhead. Warmest water? That shows up in spring. The ocean is coldest when it should, by every naive expectation, be warmest. The mechanism is wind, and it is elegant. Along the equator, the trade winds blow from the southeast. Because of the Coriolis effect, the way Earth's rotation deflects moving air, a wind blowing along the equator does not simply push surface water forward. It pushes it sideways, away from the equator, in both directions at once. The surface layer peels apart down the middle like a zipper. Water has to fill that gap from somewhere, so it rises. Cold, nutrient-rich water from a few hundred feet down, water that has been sitting in the dark, climbs to replace the warm layer that just got dragged away. We call this upwelling, and it is one of the most important processes in the ocean. It is also what feeds the fisheries of the entire Gulf of Guinea. This year, the trade winds strengthened. The peeling got more aggressive. More cold water came up than usual. No exotic physics, just wind doing what wind does, and the deep ocean rising to fill the hole. But the interesting part is not how the water goes cold. It is what happens in the air above it. Here is the thing to hold on to. The atmosphere does not care whether water is warm or cold in the abstract. It cares about one question. Where does air rise and where does air sink? Warm ocean makes air rise. Water evaporates, moist air climbs, it cools, moisture condenses into towering cumulonimbus clouds, and you get thunderstorms. Cold ocean does the reverse. Less evaporation, less rising, and the air column above it becomes stable and heavy. Crucially, because the atmosphere is a closed system, every region of rising air is paired with regions of sinking air somewhere else. Move the rising, and you move the sinking with it. Now let's apply that to what is happening right now. El Niño has taken an enormous volume of rising air and thunderstorm activity and dragged it east into the central Pacific, over open water where it does not normally sit. That is what an El Niño does. It relocates the engine. The compensating sinking air has to go somewhere, and part of it lands over the tropical Atlantic. At the same time, the Atlantic has gone cold on its own account, which independently suppresses rising air locally. Two completely separate mechanisms, one remote, driven by an ocean thousands of miles away rearranging global circulation, one local, driven by cold water right at the surface, both arriving at the same place, doing the same thing, pressing the Atlantic atmosphere down. The meteorologists at Severe Weather Europe, who flagged this combination early, called it an atmospheric shield. Not an official term, but it describes the geometry accurately. Higher pressure, sinking air, stronger wind shear aloft. Less rainfall across the exact stretch of ocean where Atlantic hurricanes are supposed to be born. But let's be precise about what that means, because this is where these stories usually go wrong. There is a stretch of the Atlantic that forecasters call the main development region, a belt from the West African coast across to the Caribbean in the deep tropics. African easterly waves roll off the continent every few days in summer, drifting out over the ocean. Most do nothing. A few find the right conditions: warm surface water to supply energy, rising moist air to build structure, calm winds aloft so the system does not get sheared apart before it stabilizes, and they organize into the hurricanes that make landfall weeks later. The current setup removes all three ingredients at once. The water is colder in the eastern part of the region. The sinking air suppresses convection. The wind shear from El Niño tears at anything that does start to spin. This is why NOAA revised its seasonal forecast downward and stated plainly that both patterns are working in the same direction. But a suppressed season is not a canceled season. It takes one storm finding a gap in the shield over water that remains historically warm closer to the American coast to make the year memorable for whoever it hits. Quiet seasons have produced catastrophic landfalls before. Fewer storms is a statement about the average, and nobody experiences the average. Now, here is the part almost every story about this misses, because it does not involve American coastline. The same band of cold water sits directly beneath the engine of the West African monsoon. The temperature of that surface controls how much moisture rises off it, and that moisture is what gets carried inland to fall as rain over the Sahel, the belt of semi-arid land running across the continent south of the Sahara. For the hundreds of millions of people living there, the difference between a warm phase and a cold phase is not a curiosity in a weather briefing. It is the difference between a harvest and a failed one, across a region where rain arrives in a single short season and does not come back if it misses. This is the reason the Atlantic zonal mode has been studied at all. And it is the reason the model bias we mentioned is more than an academic grievance. We are worst at predicting the basin where the forecast matters most to the people with the least margin for a bad year. A quieter hurricane season in the Atlantic is good news for the American coast. It is not automatically good news for everyone standing around the same ocean. So here is the shape of what just happened. Two oceans, on opposite sides of the planet, running opposite anomalies for entirely unrelated reasons, and the atmosphere between them added the signals together instead of splitting the difference. We spent this year watching one ocean very carefully. The other one changed while we were not looking, and it turned out to matter just as much. The Pacific side is well understood. The Atlantic side sits in the blind spot of every model we have, and the people who most need that blind spot fixed are not the ones with storm shutters and insurance policies. They are the ones watching one sky, waiting for one season of rain. Two oceans, one atmosphere, and the atmosphere does not average, it accumulates.